Okay, now that we know the formula for the unknowns of the exponential growth model, let us try to solve some problems to use this formula so that we know how to use this formula. Okay, so given values of the formula, a is equal to pe raised to rt, we need to find the missing quantity by substituting our given values. So that's our exercise for this video. We will try to find the unknown variable given the known values of the equation. So for letter A, we have P is equal to 680,000. And then our next known variable is the rate of the growth, which is 12%. And then our T is equal to 8 years. Now, again, for the exponential growth model, we only have 4 variables. We have A, P, R, and T. E here is the Euler's constant, which is roughly or approximately equal to 2.718. So given P, R, T, what is our unknown variable? Our unknown variable is A. And A is very easy to solve. We just have to use this formula here, which is A equal to PE raised to RT. And what do we have to do? We just have to substitute the given values. So that gives us the equation 680,000 times the Euler's constant raised to R. Now, R here is given in percentage, but if we're going to use R in our equation, we have to use its decimal form. So the decimal form of 12% is equal to 0.12. Move the decimal point 2 spaces to the left. So it gives you 0.12. So that's the value that we're going to substitute for R in our exponential growth model. So that's e raised to 0.12 times the years, or the time, which is 8 years. Now, plug in this equation in our scientific calculator, and this would give us a value for our growth after for our population after the growth at 1,775,953.60. Okay, very easy, very easy. It's just a matter of us substituting the variables. Now, what if we have to solve for another unknown variable? So let's move this so that we have space. What if we have to solve for another variable? Let's say for letter B, we have A is equal to 1,240,000, and then our next known variable is the rate at 8%, and our time is 30 years. Now, what is our unknown? It's very obvious that our unknown is the initial population. We have A, we have R, we have D, but we do not have P. And what is the formula for P? P is equal to the population after the growth divided by the Euler's constant raised to RT. So writing down the formula, that's P is equal to A all over E raised to RT. Now, again, it's just a matter of us substituting the variables, our known variables. So this would give us 1,240,000 as our numerator divided by the Euler's constant raised to the rate of the growth. Again, our rate of growth is given in percentage form. We have to use the decimal form, so that's just 0.08. Move the decimal point 2 spaces to the left. Okay, and that's 0.08. So E would be raised to 0.08 times 30 years. And now it's just a matter of us plugging in this equation in our calculators, which would give us a value of 112,490.26 as our initial population, given this values that we have here. Okay, so this is our final answer given our known values of A, R, T. Okay, so let's move on to another example. Now, what if we have to solve for the rate? Okay, what if we have to solve for the rate? So at letter C, we have the given values of A is equal to 786,000, B is equal to 247,000, and T is equal to 17 years. Now, again, our unknown variable is R, right? We only have 4 variables, A, P, R, T. And since R is not given, so R is our unknown variable. And how do we solve for R? We solve for R using the formula R equals to the natural logarithm of A over P divided by the time. Okay, let me erase this. Let me just write that down properly. Okay, so the R is equal to the natural logarithm of A divided by P all over the time. Okay, so given the known variables, what we just have to do is to plug in our known variables. So that gives us R is equal to the natural logarithm of 786,000 divided by 247,000 all over the given time, which is 17 years. So plugging in this equation in our calculators, one thing we have here is trailing zeros, so you could just simply plug in 786 all over 247 to minimize the process in inputting this equation in our calculators. So this would give us an answer of 0.0681. So this is the rate of the growth. But this answer, no, we could have this as final answer. That's totally okay. But if we want our final answer in decimal form, then this would give us 6.81% as the rate of the growth of our problem, given the values of A, P, and T. Okay, essentially, to solve for T, it's just the same process of using the natural logarithm of A over P, but instead of dividing dividing it by R, we dividing it by the time, we divide it by the R. Okay, sige, let's have a problem where T is our unknown. Okay, where T is our unknown. What if, let's have D, what if our given values are A is equal to 5 million and then P is equal to 1 million? Okay, and then since T would be our unknown, our next known variable is our R, which is 64.5%. Now, again, the formula for T looks the same as the formula for R, but instead of dividing it all over by T, we divide this all over by R. Okay, so our equation now would look like T is equal to the natural logarithm of 5 million all over 1 million, which is the initial population, divided by the rate of the growth. But again, if we're using R in our equation, it has to be in the decimal form. So 64.5% here would become 0.645. And that's our denominator. That's 0.645. Again, when we plug it in our calculators, these trading zeros we could cancel out. So essentially, our numerator would be the natural logarithm of 5 over 1, or no, that is just the natural logarithm of 5 divided by 0.645. Now, plugging it this plugging this into our scientific calculators will give us a time of 2.50 years as our time of growth, given these values A, P, and R. And that is how we use the formula of our variables and our exponential growth model.